All right, welcome everyone. Right now, we'll get started looking at the multiple variable version of the chain rule. Okay, so let's take a second here. Let me bring in my doc cam and we'll get going. All right, so here we go. The chain rule for functions of several variables, right? So as we've been starting off in discussion of this chapter, I always go back to what we would do, how we introduce some of these concepts, topics in our first semester calculus course. Okay, so recall back in Calc 1, our 20A discussion, right? Our chain rule, this was our kind of differentiation rule. For the composition of functions, right? When we had some f composed with g at x, or f of g of x, that composition, this function f depends on what this result for g of x gives us, right? So f depends on g of x depends on x, what value of x we're choosing. And so when we took that derivative, d dx, since there's only one variable truly that this composition depends on, if you evaluate, you just get an expression of x. That's what we're using our regular derivative here. There's only one independent variable, x, that we're choosing. F depends on g depends on x alone. And so when we did that derivative, right, remember we would take f prime, the derivative of the outer function, and then multiply by g prime of x, right, that inner function's derivative. And we identified, we maintained that same kind of interior expression, that interior function, that derivative of the outer f prime depends on g of x still. And then we took the derivative of the inner function like so, okay? So that composition, that the f depended on g, when you took that derivative, kind of whittling our way down, peeling back those layers of the onion, all those little phrases we would use. Take the derivative of the outer function, f prime, keep the same g of x inside, then take the derivative of the inner function, multiplying those together. So now, for our multivariable functions in Calc 3, right, our 20C course now, so, right, we have functions with more than one possible independent variables. Right, so we had that z is a function of xy, right? So as we talked about here, z depends on both x and y. So in that case, so we identify our partial derivatives. Now this is what we did in introduction to those partial derivatives before. Identify partial derivatives to measure, to compute, to find the rate of change, right? That derivative with respect to just one of those two variables. And we saw, right, dz dx, that little curly d, if you will, for that partial, right, that f sub x, dz dy, f sub y, in that notation. Okay, so now, with that said, where the chain rule comes in, right? Well, what if both x and y in that function depend on another variable or parameter? So for instance, what if that x is actually a function of t? Think about when we parameterize our curves in space, right? For any moment t, we can find our x and y location and later z location, right? What if that's the case? So in that instance, let me take this page away. What if instead we're looking at z as a function of x of t and y of t? So in this case, we can see that z or f depends on both x and y. Then x and y depend on t. So it's very much like that chain rule discussion we had here. F depends on g, g depends on x, right? So now in this case, f depends on x, x depends on t. So when we start to work on then, so for that derivative, of that function z is equal to f of x, y, okay? If there's that further dependence, when you look at that derivative, we need to consider those rates of change for each component variable in order to find our, what I might call our full derivative. Not technical language here. But for instance, what if we want to find the derivative of z with respect to t? Okay, some information here. T is kind of like that final independent variable. There aren't any other variables that x or later on f can depend on, right? So in that case, we use that kind of full derivative d dx, right? Not that partial derivative notation. Because there's no other variables for that function to depend on besides that t. So there's no need for the part, so we get that full derivative that's kind of strict derivative, right? So when we look at taking that derivative with respect to t on both sides then, right, of that z function, x of t, y of t, like so, right? If we take that derivative on this side, right, we're going to get our dz dt, that derivative. And now this is when our chain rule shows up. The outer function is that f. The inner function, or plural, inner functions, are going to be the x of t, y of t, right? Because, right, x depends, or f depends on x, and then x depends on t. So really there's kind of like this middle layer. But when we start to go through, taking that derivative, what are we going to find? We're going to start off with, okay, I can't take the derivative of f with respect to t directly. We first see that f depends on x to begin with. So that outer function, f prime, or here my df dx, right? And then from there, now the derivative of x comes out, since x only depends on t, dx dt. So notice we have this mix, partial, full derivative, if you will, right? There's only one variable that x depends on, and we're getting that derivative here. And then now, because there's dependence on t over here, since that's where I'm taking the derivative with respect to t, I want to see where do all of those t's show up. It showed up in the x, but it also showed up in the y. So I have to also include the derivative of f with respect to y, that partial. And then since y depends on t, only t, dy dt. So this is that kind of complete differential, that complete derivative, full derivative of that function z with respect to that particular variable parameter t. And again, if we had a function of x, y, z, or to some new function here, z, we just continue that pattern, that chain rule, building our way out, adding for those components. Okay? And so, for an example, let's jump to it, borrow a problem from our text. And we check out this problem, problem number, let's see here, something that's going to work not too lengthy, but let's see here. This function, let's do number 2 for ease. This is on page 983 of our text that we're using for the course. We're given z is equal to x minus y over x plus 2y, where x is equal to e to the pi times t, y is equal to e to the negative pi times t. Okay, so there's my function of t, z the function of x and y. So again, realistically, it might create more work in terms of complications of all these different expressions involved, but we could just make that substitution, let x take on the e to the pi t, y be e to the negative pi t, go through that work, right? Everything's in terms of t alone. But let's use this chain rule to find that dz dt, how z is changing with respect to t. Okay, so here we are. So if z is equal to x minus y over x plus 2y, my function f of x and y, x minus y over x plus 2y, x of t e to the pi t, y of t, e to the negative pi t, right? And so kind of utilizing my notation up here, when I look at my df dx, I know I'm going to need some more space. So instead of trying to compact it up here, let's put that information below. So I take that derivative with respect to x, right? Y is a constant, x is the variable. It's still a quotient rule. So here we go. So the derivative of the numerator with respect to x is 1 times the denominator x plus 2y minus numerator x minus y. Derivative of the denominator 1. 2y is a constant, that goes away. Derivative of x 1. That's all over our denominator x plus 2y squared. So we're going to get here x minus x goes away. Negative, negative makes it plus y, 2y plus 1y, 3y over x plus 2y quantity squared. So this is that df dx, my partial of f with respect to x, my partial of f with respect to y. Which one again? Derivative of the numerator with respect to y, negative 1. That x is just a constant, it goes away. Denominator x plus 2y minus numerator x minus y. Derivative of the denominator, x is a constant, 0. Derivative of 2y, 2. Over that same denominator, x plus 2y squared. Distribute the negative 1 in. Okay. Let me do this one a little bit more carefully. Distributing the 2 and the negative, minus 2x plus 2y over x plus 2y quantity squared. The 2y goes away. Negative x, negative 2x minus 3x over x plus 2y squared. Again, those don't have to be identical. They're probably not going to be identical. We just want to keep track of those terms. Up top here, we got dx dt, chain rule, e to the pi t times pi, or pi e to the pi t. Dy dt, y only depends on t, e to negative pi t times negative pi, or negative pi e to the negative pi t. So there's my dx dt, dy dt, respectively. So then when I look at my dz dt, remember in that formula, taking our derivative of z, or our function, with the first dependency it has, it first depends on x, df, or not df, dx, but then that x depends on t, so there's our product dx dt, plus now z or f, the next variable it sees is y, but that y depends on that y sees what t is doing, so we need that dy dt afterwards. So I'm kind of scanning that function. Okay, z sees x, I need a partial with respect to x. Z sees y, right? Depends on y, so I need a partial with respect to y. But that x and y both depend on t, so we need to incorporate that portion of the derivative, that chain rule, going forward. Okay. All right. So now plugging in then. Df dx, 3y over x plus 2y squared, dx dt, pi e to the pi t, plus df dy, negative 3x over x plus 2y squared, negative pi e to the negative pi t. And so I'm going to stop here for a moment just to see those components in place. But looking at our expression, now we could replace, substitute in that x and y, make sure it doesn't look like the word any, and y as their expressions in t, right? X was equal to e to the pi t, y was e to the negative pi t, then simplify to see how those expressions may work together, simplify out, if at all. But we could do that work. Okay. All right. And likewise, up here, we could have replaced x and y with those expressions and just taken it with respect to t like we would do in 20a. But we're hoping by separating, by partitioning out those different expressions and functions as they are represented, maybe using those kind of partial derivatives, internal derivatives, right? Kind of mixing that language of chain rule, we can help organize those components. Okay. And so then, with that said, our chain rule, when we see that those interior functions just depend on one variable, t, we have that full derivative, right? But then now, in this next discussion, it may be possible for our, we'll say, inner functions to depend on more than one variable or more than one parameter. We start to use that word parameter a little bit more, right? So you might get this function z is a function of x, which is now a function of both s and t. Y is a function of s and t, right? Depend, x and y depend on both s and t. So, right, we're just expanding out, adding more layers, if you will, for that derivative. Okay. And so, said, when we look at taking those derivatives, then, since there's more variables that those depend on, x and y, it doesn't just depend on t this time, right? Now, because we have that extra dependence, we will use that partial derivative notation throughout. Right, in that previous discussion, our time, we use that kind of full derivative because x and y only depended on t alone. There's no other variable that can cause a change in that function, in that quantity. So it gets that full derivative. Now, because x can depend on s and t, even though I'm looking at the derivative with respect to s, that quantity t is still there as a possible way of altering, changing what this value for x can become. So then when we start to look at our derivatives, when I take now partial of z with respect to s, right? Thinking about that, we take our partial of f as it sees x, but then x depends on s. And there's also F's dependence on Y, but then Y has a dependence on S. And even further, right, we can even layer that more. If S and T depend on another parameter, U, V, we can take the derivative of Z with respect to U or V, right? Just kind of keep on building with those chain rule discussions. And then likewise, dz dt, taking our partial of f with respect to x, but then x has a dependence on t. df dy, but then y depends on t as well. Or again, partial because y depends on both t and s. So when I look at the derivatives, I have to take a partial. So I'm only looking at one particular variable that we're allowing to vary, that we're allowing to change. Okay. And so we can start to organize just like we did that last example. It's just now recognizing that there might be another variable to consider in those derivatives. Okay. All right, I'll leave it as a kind of short discussion here. We can look at examples from the text. If you have any questions, of course, let me know.